Okay, we're looking at number 4. They have a reaction up here, and they give us the equilibrium concentrations of everything. And remember, that's good news, because if we know the equilibrium concentrations, we should be able to calculate the equilibrium constant. I also am noticing they're giving us a delta H, so maybe we'll use that a little bit later. So the first step, just write the expression for Kc and calculate its value. So they're talking about a general equilibrium expression. So I've written 2 equilibrium expressions, and so I want you to think about first which of these 2 is the more appropriate format, because they're probably going to care. You notice they both have products over reactants, but when you're trying to decide should you write a Kc or Kp, you notice that they gave us the equilibrium concentrations, and they were concentrations, not pressures, right? Not atmospheres. So we definitely are going to go with the top one. If you wrote the bottom one, they would mark it wrong. In part B, they want us to calculate the delta G for the reaction. Well, that's not too hard if we know the K value, because we know that delta G is equal to the negative RT natural log K. So we just have to figure out the equilibrium constant. Alright, so I plugged in the values for the equilibrium concentrations of these guys into the equation, and I got a Kc value of 10. So now I'm ready to plug in the K into Gertlink, and that's what it looks like. They said it was at 570 K for the temperature, and remember R here is 8.314 because we want the units to be in joules. And so after I plugged in, I was going to say, remember that the R value has got to be in joules, so that's why it's this one. And I got 10,911, and remember that is going to be in joules here. So let's see if they asked for any. Nope, they didn't ask for any particular unit. So we can keep in joules as long as we keep that unit consistent. And then let's go back and think about sig figs. All these look like they had 2 in it. We had more than 2 here. We had 2 there. So I'm going to drop this down to 2 sig figs. So 11,000 joules, or of course you could say 11 kilojoules if you wanted to. Alright, so they're asking us to describe how the concentration of hydrogen will be affected by some changes that we're doing here. Probably most of these are Le Chatelier shifts, right? So there's hydrogen. We want to know is if it's shifting to the left, then we'll make more hydrogen. If it's shifting to the right, we'll make less hydrogen for each one of these. Now, I hate to say it, out of the interest of time, since I'm a little behind on these videos, I'm not going to write out the answer, so I'll describe them verbally. So first of all, if you're going to figure out if the temperature has an impact on hydrogen, you remember that you actually need to include energy in the reaction. Now, given that this is an exothermic reaction and energy is released, I'm going to put energy on the product side, since energy is going to be released. Now that we know that energy is on the product side, if the temperature is increased, that will be an increase in energy. It will shift the reaction to the left, and we should increase our concentration of hydrogen. And that's the way you would want to describe it. Make sure you mention that energy is on the product side, and therefore an increase in energy will shift the reaction to the left, increasing the concentration of hydrogen. The other thing I'm going to point out here that maybe wasn't asked in the question but is useful to know is, all these other changes may shift the reaction to the left or the right. In other words, they may increase or decrease the amounts of hydrogen. But temperature should be the only one that actually changes the K value. You'll remember that temperature is the only one that does that. In part 2, they want to know which way it'll shift things if the volume of the chamber is increased. So you remember that if we have a reaction chamber with some gases in it, which are our gas reactant component, and if we increase the size of that chamber by pulling up a piston or something else, the gases will spread out. Momentarily, it'll be a decrease in pressure. And of course, the system will want to fix that. So in order to get the pressure back to where it was, it's going to shift to the side with more moles of gas. And the side of more moles of gas looks to me like this side, because we have 3 moles of gas there and 1 mole of gas there, and only 2 over here. So I think to increase the pressure back up, it's going to shift to the left. And so we should, again, see an increase in the amount of hydrogen that's made. Let's look at part 3. Nitrogen gas is added to the chamber. Well, nitrogen gas is a gas, it's not a solid. You remember, if things are solid, they will not impact the equilibrium because they don't show up in the equilibrium constant. But nitrogen is a gas, and it is in the equilibrium constant. So an increase of a reactant will shift the reaction to the right, And of course, if it goes to the right, it's going to actually consume some hydrogen as it does that. So we should see a decrease in the amount of hydrogen that's there. All right, and lastly, there's helium. And I won't go to a new slide for this one because this one's pretty easy. Helium would have no impact on the concentration of hydrogen because it will not shift the reaction either way. The reason is because helium is not in the equilibrium expression. Now, you might think, well, helium will increase the pressure and won't that cause things to shift left or right? But you got to remember that it won't change the partial pressure of any of these. And it's kind of a weird thing to talk about anyway. If it doesn't show up in the equilibrium expression, it won't shift the reaction either way. And you remember that when we talked about this in class, they referred to this as an inert gas. And the best explanation for why inert gases don't affect equilibrium is they are not in the equilibrium expression.